Okay, now we're going to talk about chapter 11, which is reaction rates and chemical equilibrium. And it's going to start off by talking about something we've already talked about briefly, which is the energy of reactants and products. So when you undergo a chemical reaction, you typically have reactants that start out at a certain energy, and then an activation energy is supplied, and this leads to the reaction proceeding and leading to products which are at a new energy, in this case, a lower energy. The way that we talk about chemical reactions is using something called collision theory, which is similar to kinetic theory, except it goes a couple steps further. So a chemical reaction occurs when collisions between reacting molecules provide sufficient energy to break the bonds. Another requirement is that molecules collide with the proper orientation. And the third requirement is that the bonds between atoms in the reactants are broken and new bonds form. In the case of the reaction shown, the bonds broken are the ones between nitrogen atoms in a nitrogen molecule and oxygen atoms in an oxygen molecule. And they collide in the right orientation. This provides the energy for them to split into two nitric oxide molecules. So, based on those criteria, a chemical reaction will not take place if the collisions between reacting molecules do not have sufficient energy to break the bonds. So, in any reaction mixture, there will obviously be a distribution of particle energies because the temperature only gives you the average kinetic energy. So there will be some that are high energy and some that are low energy, and so the rate of reaction will change based on the available energy. Another time when reactions will not occur is if the molecules are not properly aligned. So in the case of nitrogen and oxygen reacting, if they strike each other so that they're both oriented vertically, then the nitrogens and oxygens will come in close proximity to one another at the same time, and this will cause the new bonds to form. But if there's not sufficient energy, that reaction will not occur, and therefore you'll be left with a nitrogen molecule and an oxygen molecule that have bounced off of each other. And then obviously in the situations with the wrong orientation, here you have them approaching each other end on. However, because the orientation is wrong, two of the atoms cannot interact with each other, and therefore the reaction can't occur. And then in the case where they are differently oriented, there is none of the atoms encounter each other in the right orientation, and they bounce off of one another as well. So this brings us to the concept of activation energy, which is the minimum energy required for a reaction to take place upon proper collision of reactants. So in the case of the reaction between nitrogen and oxygen, the reactants have a lower energy, and you have to hit them together very hard in order for them to react, and then they fall to products which have a higher energy. Energy implies temperature, so the rate of a reaction determines the speed at which reactants are used up, or the speed at which a product forms. This reaction rate increases as the temperature rises because higher temperature means that the molecules are moving faster, and they will provide their collisions with the energy of activation. The higher the temperature, the faster the reaction rate in general. So here is another relation. Reaction rate is also related to concentration, because if you can imagine, if you increase the concentration of reactants, then this increases the number of collisions, and if there are more collisions, then statistically more reactions will occur in a shorter period of time, which will increase the rate. So Here is an illustration of that. If you have one particle of reaction, one particle of reactant of each reactant, that means there's one possible collision between this particle and that particle, and the reaction rate will be slow. Now, if you have two of one reactant and one of the other reactant, then now you have two possible collisions. So both of those reactant particles can collide with the second one, and they have equal probability, which means that the reaction rate is slightly faster. Now, if you have two particles of each reactant, then they can each collide in 4 different ways, which increases the rate even further. Now, there are ways of reducing the activation energy required, and we use something called a catalyst to do this. This generally speeds up the rate of reaction by lowering the energy of activation, and catalysts are typically not used up during the reaction. So something like a platinum surface in a catalytic converter in a car will speed up the reaction of carbon monoxide to carbon dioxide, and also it will help react nitrogen molecules like nitric oxide or NO2 into harmless gases like nitrogen and oxygen again. Also, in your body, there are enzymes, which are basically proteins that help other biological reactions happen. And they're also not used up in the process, but they greatly speed up the rate of those reactions to a point where life can occur. So, just to summarize, if you increase reactant concentration, this will increase the reaction rate because there are more collisions. If you increase the temperature, this will also increase the number of collisions, but will also increase the number of collisions with the proper activation energy, which will increase the reaction rate. And adding a catalyst will lower the energy of activation, which will increase the number of collisions that have the appropriate amount of energy, and this will increase the reaction rate. So we're going to do a quick learning check. State the effect of each on the rate of reaction. So increasing the temperature will increase the reaction rate. If you remove a reactant, this will decrease the reaction rate because it decreases the concentration. If you add a catalyst, this will increase the rate of reaction. If you place the reaction flask in ice, this will lower the temperature, which will decrease the rate. And if you increase the concentration of one of the reactants, you will increase the rate because you will increase the number of collisions. Another example, using a real process. Indicate the effect of each factor listed on the rate of the reaction as increases, decreases, or no change. So the reaction is 2 carbon monoxide molecules react with an oxygen molecule to form 2 carbon dioxide molecules. So if you raise the temperature of this reaction, it will increase the rate. If you remove oxygen, it will decrease the rate. If you add a catalyst, it will increase the rate. And if you lower the temperature, it will decrease the rate. So there are something called reversible reactions, which occur in both the forward and reverse direction. An example of this is the reaction of sulfur dioxide and oxygen. When they collide with each other, the forward reaction begins, which produces sulfur trioxide gas. However, as you form sulfur trioxide molecules, they can begin to collide with each other and therefore form reactants again. So we write this reaction with a double arrow to indicate the forward and reverse reactions occurring simultaneously, like so. Now, the idea of reversible reactions brings about the concept of chemical equilibrium. So at equilibrium, the rate of the forward reaction becomes equal to the rate of the reverse reaction. And once this occurs, the forward and reverse reactions continue at equal rates. And this leads to no further change in the amount of reactant and product. So this can be useful when you are doing chemical reactions. When you reach a certain equilibrium, there won't be any further change and the reaction can be considered complete. However, you may not have 100% what you want in your reaction mixture. So here's an example. For the reaction at equilibrium, hydrogen gas plus iodine gas yields 2 hydrogen iodide gas molecules. The forward reaction between hydrogen and iodine forms hydrogen iodide. The reverse reaction is 2 hydrogen iodide molecules forming a hydrogen molecule and an iodine molecule. And at equilibrium, the amounts of these are constant. Now here's a picture of this happening. So at 0 hours at the start of the reaction, you have all reactants. You have 4 moles of hydrogen and 4 moles of iodine and 0 moles of products. So the rate of the forward is very fast and the rate of the reverse reaction is non-existent. Now after 1 hour, you have produced 2 moles of products, which means that you only have 3 moles of each reactant left. And the forward reaction has slowed down a bit, and the reverse reaction has begun to occur. Now, say after 2 hours, you've produced another 2 moles of hydrogen iodide, so for a total of 4, meaning you have 2 moles of each reactant left. Now the forward reaction has become slower, and the reverse reaction is even faster. After 3 hours, now you're down to 1 mole of each reactant and 6 moles of product, and the rates of forward and reverse reactions are equal. And it will remain this way even if you wait for 24 hours. The number of moles will not change. Even though the reaction is continuously occurring, the balance does not shift in one direction or the other. So, quick study check here. Write the forward and reverse reactions for the following. So, you have methane gas plus hydrogen sulfide gas yields carbon disulfide gas and hydrogen gas. So, the forward reaction is just the same. Methane plus hydrogen sulfide yields carbon disulfide and hydrogen gas. The reverse is carbon disulfide plus hydrogen gas yields methane and hydrogen disulfide. Hydrogen sulfide gas. So once we've gotten to equilibrium, we can start to quantify the amount of chemicals present. So say you have a hypothetical reaction, A moles of molecule A going to B moles of molecule B. We can develop something called the equilibrium constant expression, or Kc, which gives the concentrations of the reactants and products in brackets at equilibrium. So Kc is defined as the concentration of B to the power of the number of moles of B divided by the concentration of A to the power of the number of moles of A. And this is products divided by reactants. Square brackets indicate moles per liter of a substance, and the coefficients B and A are superscripts that raise the moles per liter to a specific power. So you can write Kc expressions for any reaction. You start by writing the balanced equilibrium equation. Then you write the products in brackets as the numerator and the reactants in brackets as the denominator. You do not include pure solids or liquids because their concentration doesn't change. And then you write the coefficient of each substance as an exponent. So we're going to do an example. Write the Kc expression for this reaction between carbon monoxide and oxygen at equilibrium. So first, you write the balanced equation. 2 carbon monoxide molecules plus an oxygen molecule yields 2 carbon dioxide molecules. Then you write the products in brackets as the numerator and the reactants in brackets as the denominator. So the concentration of CO2 gas divided by the concentration of CO gas times the concentration of oxygen gas. And then you write in the coefficient of each substance as an exponent. So carbon dioxide gas is squared, as is carbon monoxide gas, but oxygen appears in 1 molar quantity, so it is to the first power. So that is our equilibrium expression. Now, see if you can identify the correct Kc expression for this reaction between nitrogen gas and chlorine gas to form nitrogen trichloride gas. So the 4 options are shown here. The first one has nitrogen trichloride on the top with nitrogen times chlorine on the bottom. Second one has nitrogen times chlorine to the 3rd power on top and nitrogen trichloride to the 2nd power in the denominator. The third option has nitrogen trichloride squared in the numerator and nitrogen cubed times chlorine in the denominator. And the 4th option has nitrogen trichloride squared in the numerator and nitrogen times chloride cubed in the denominator. Now, if you remember, the way we solve this is we write the balanced equation. We have 1 nitrogen plus 3 chlorines yields 2 nitrogen trichlorides. Then you write the products in brackets and as the numerator and reactants in brackets as the denominator. So the products are nitrogen trichloride and the reactants are nitrogen gas and chlorine gas. So they've arranged as this. And then the coefficients of each substance become the exponents. So nitrogen trichloride is to the 2nd power, and chlorine gas is to the 3rd power. So that would be option 4. Now, we don't always have equilibrium with everything in the same phase. So we have to introduce the concept of heterogeneous equilibrium, where you have gases, solids, and or liquid states as part of your reaction. A good simple example of this is the reaction of sodium bicarbonate to produce sodium carbonate and carbon dioxide and water. This is something that occurs if you heat baking soda in an oven. This reaction will occur. The concentration of solids doesn't change, so they're not included in the equilibrium expression. However, there are 2 gases in this reaction, both in the products. If we remember correctly, products go in the numerator, so the concentration of carbon dioxide times the concentration of water vapor is equal to the equilibrium constant expression for this reaction. Basically, this reaction will just occur until all of the reactants have reacted into products. Here is another example. What is the Kc expression for the following reaction between potassium chlorate and going to potassium chloride and oxygen? So, first option is the concentration of KCl times the concentration of oxygen divided by potassium chlorate. Second option is potassium chloride squared times oxygen cubed divided by potassium chlorate squared. The third option is potassium chloride squared times oxygen cubed. And the fourth option is oxygen cubed. Now, if you'll notice, the only member of this reaction that is not a solid is oxygen gas. It is a product, so it goes in the numerator, and it has a coefficient of 3. And so the correct equilibrium expression is obtained as Kc equals O2 to the third power, which is option 4. So based on this, we can generate an algorithm for calculating Kc values. So you start by writing the Kc expression for the equilibrium, and then you substitute equilibrium concentrations into the expression to calculate the Kc. For example, calculate the equilibrium constant for the reaction mixture at equilibrium of hydrogen gas plus iodine gas reacting to form hydrogen iodine gas. So the concentrations are at the start 1.2 moles per liter of hydrogen gas and 1.2 moles per liter of iodine gas. The concentration of hydrogen iodide gas is 0.35 moles per liter at the start. So the equilibrium expression is obtained by putting the products in the numerator and the reactants in the denominator and applying the correct coefficient powers, and then substituting in the molar concentrations. So the concentration of hydrogen iodide is 0.35 moles per liter, and that is squared. And you divide that by 1.2 moles per liter times 1.2 moles per liter for the hydrogen and the iodine. And we obtain that the equilibrium constant is equal to 8.5 times 10 to the minus 2. Here is another example. What is the equilibrium concentration for the reaction of methane and water to form carbon monoxide and hydrogen gas? So at equilibrium, the concentrations are 0.13 molar methane, 0.81 molar carbon monoxide, 0.53 molar water vapor, and 0.28 molar hydrogen gas. So the options are 0.26, 3.3, and 3.9 for the value of the equilibrium constant. We calculate this by setting up our equilibrium expression. Carbon monoxide and hydrogen are in the numerator, methane and water vapor are in the denominator, and our concentrations when substituted in, 0.81 times 0.28 cubed divided by 0.13 times 0.53 is equal to 0.26, which is answer A. Here is our reaction again with sulfur dioxide and oxygen to make sulfur trioxide gas. Now this reaction will contain mostly SO3 gas at equilibrium with small amounts of oxygen and sulfur dioxide. Even if you start with only sulfur trioxide, some of it will react with itself to form oxygen and sulfur dioxide at equilibrium. Likewise, if you start with only SO2 and oxygen, it will evolve to produce a solution that contains mostly sulfur trioxide with a little bit of the two reactants present. So this means that equilibrium can favor either the forward or the reverse reaction. So if equilibrium is reached after most of the forward reaction has occurred, the equilibrium system favors the products. So in this case, no matter where we start, the equilibrium conditions are the reaction to be mostly gone into the forward direction, meaning that this reaction favors products. So this means that the equilibrium constant is large. So a large equilibrium constant produces a large amount of reactants, a large amount of products, and very little reactants remain. So our reaction from before, nitrogen trichloride coming from nitrogen gas and chlorine gas, that has an equilibrium constant of 3.2 times 10 to the 11th power. That's astronomically large. This means that if you react nitrogen and chlorine gas, it will go almost entirely to nitrogen trichloride with very little nitrogen or chlorine left over. Now, equilibrium can also favor reactants. So if equilibrium is reached after very little of the forward reaction has occurred, then the equilibrium system favors the reactants. A good example of this is the reaction of nitrogen gas with oxygen gas to form nitric oxide. Initially, you have even amounts of nitrogen and oxygen. The forward reaction occurs a tiny amount to produce a very small amount of nitric oxide. And also, if you start with only nitric oxide, then the reverse reaction will occur until a large amount of nitrogen and oxygen are present. So if equilibrium favors reactants, that makes the equilibrium constant very small. So for this reaction, NO squared divided by N2 times O2 is equal to 2.3 times 10 to the minus 9. So essentially, almost no products will be present at equilibrium. So here's a summary. If the equilibrium concentration is 1, then there will be roughly equal concentrations of products and reactants. However, if the Kc is large, then it will favor products, and the reaction will essentially run to completion. And if it favors reactants, then the reaction will barely take place. Here are a few examples. So the reaction of carbon monoxide with oxygen to produce carbon dioxide has a reaction constant of 2 times 10 to the 11. It favors products. Hydrogen gas plus S2 gas produces hydrogen sulfide gas. This has also a large Kc value of 1.1 times 10 to the 7th. So that will favor products as well. The reaction of nitrogen gas with hydrogen gas to produce ammonia has a large but not as large equilibrium constant of 1.6 times 10 to the 2. This will also favor products. However, the reaction of phosphorus pentachloride with itself to produce phosphorus trichloride and chlorine gas has a reaction constant of 1.2 times 10 to the minus 2. So this reaction will favor reactants. And likewise, the one we just discussed, nitrogen plus oxygen to get nitric oxide, has an equilibrium constant of 2 times 10 to the minus 9, meaning it will favor reactants as well. Here is a quick learning check to see if you've internalized that information. Indicate whether the reaction mixture equilibrium contains mostly reactants or mostly products. So reaction A is the reaction of hydrogen plus fluorine gas to produce hydrogen fluoride gas. It has an equilibrium constant of 1 times 10 to the 95th power. And reaction B is the reaction of 3 oxygen molecules to produce 2 ozone molecules, and that has an equilibrium constant of 1.8 times 10 to the minus 7. So it can be seen that part A has a large equilibrium constant, it will favor products, and question B has a small equilibrium constant, so it will favor reactants. So you can also start from your equilibrium constant and calculate the equilibrium concentration of a reaction. So if you know the equilibrium constant and the concentrations of all but one of the reactants and products, you can calculate the concentration of the remaining substance. Like always, we have an algorithm to guide us through this process. Step 1 is write the Kc expression for the equilibrium equation. Step 2 is solve the Kc expression for the unknown concentration. Step 3 is substitute the known values into the rearranged Kc expression. And step 4 is check your answer by using the calculated concentration in your Kc expression to make sure that you get the same number. So, examples. At equilibrium, the reaction phosphorus pentachloride going to phosphorus trichloride and chlorine gas has a Kc value of 4.2 times 10 to the minus 2. And we also are given the concentrations of phosphorus trichloride and chlorine gas, which are equal to each other at 0.1 molar. Given that information, what is the concentration of phosphorus pentachloride at equilibrium? We start by writing our equilibrium constant expression for this particular equation. So we have products in the numerator and reactants in the denominator, and there are no coefficients greater than 1, so the powers are all equal to 1. Now we have to rearrange our expression to solve for the concentration of phosphorus pentachloride. So all we have to do in this case is divide by the equilibrium constant and multiply by phosphorus pentachloride, and substitute our known concentrations into the rearranged expression. So 0.1 times 0.1 molar divided by 4.2 times 10 to the minus 2 is equal to 0.24 molar of phosphorus pentachloride. And we can check this answer by then calculating our equilibrium constant using that concentration in the denominator. 0.1 times 0.1 divided by 0.24 is equal to 4.2 times 10 to the minus 2, which is the equilibrium constant that we were given at the start. Here is another example. The equilibrium constant is 2.0 for the reaction of nitrogen, oxygen, bromide to produce nitric oxide and bromine gas. So at equilibrium, NOBr has a concentration of 0.5 molar and NO has a concentration of 0.8 molar. What is the concentration of bromine gas at equilibrium? If we start by writing our expression for the Kc, Kc is equal to NO squared times Br2 divided by NOBr squared, based on the coefficients of the reaction. Then we solve for the concentration of bromine. In this case, we have to divide Kc by NO squared and multiply by NOBr squared to get Br2 by itself. We substitute our known values into the expression, so 0.5 squared times 2 in the numerator and 0.8 squared in the denominator, which gives us 0.78 molar bromine gas at equilibrium. And step 4, we check our answer by using the calculated concentration in our expression. So 0.8 squared times 0.78 divided by 0.5 squared is equal to 2.0. So Le Chatelier's principle is a principle that we use to describe disruptions of chemical equilibrium. So you can imagine someone standing on a balance board and giving them a shove to the right. How would they fix that so they don't fall? They would shift their weight to the left. So systems in equilibrium are similar. If you perturb them in one direction, they will try to compensate by going in the opposite direction. Le Chatelier's principle states that any change in equilibrium conditions upsets the equilibrium of the system. A system at equilibrium under stress will shift to relieve the stress, and there will be a change in the rate of the forward or reverse reaction to return the system to equilibrium. So the first way we can perturb a chemical system is by adding reactant to an already occurring reaction. So say you have a reaction between A and B to produce C at equilibrium. If you add more A, then this will upset the equilibrium and cause the rate of the forward reaction to increase so that the concentration of A can go down and maintain the same equilibrium constant. So you have it at equilibrium. The constant is B times C over A. You add A, this increases the concentration of A, which would make equilibrium constant go down, but it's constant, so the concentration of B and C must increase to compensate for the increase in concentration of A. So here's a real reaction. Hydrogen gas plus fluorine gas yields hydrogen fluoride. If you add more of either hydrogen gas or fluorine gas, then you will increase the number of collisions. This will increase the rate of the forward reaction, which will form more hydrogen fluoride product, and equilibrium concentrations will again equal Kc. So the effect of adding reactant shifts the equilibrium towards the products. Now if you add a product, the opposite occurs. So if you add more HF, then there's an increase in the number of collisions of HF molecules with themselves. This causes the rate of the reverse reaction to increase and causes more hydrogen and fluorine gas to be formed. This has the effect of shifting the equilibrium towards reactants. So in summary, if you want to shift the equilibrium towards HF, you have to add more hydrogen or fluorine gas. If you want to shift the equilibrium towards hydrogen and fluorine, you have to add more HF gas. You can also remove reactants. So if you remove hydrogen or fluorine from the reaction, this will decrease the number of collisions between the reactants, which will in turn decrease the rate of the forward reaction, which will therefore cause equilibrium to shift towards reactants. And if you remove a product, this will cause the rate of the reverse reaction to decrease, which will cause the rate of the forward reaction to become greater and shift reaction towards products to maintain a constant equilibrium constant. So there's a summary of these changes. Say you have an increase, so this reaction is PCl5 going to PCl3 plus chlorine gas. So PCl5 is reactants and PCl3 and Cl2 are products. If you increase PCl3, that's shifting the equilibrium towards products, and this will produce more PCl3 and Cl2. If you decrease the amount of PCl5, this will shift the equilibrium towards reactants. If you increase the amount of PCl3, this will increase the rate towards reactants. If you decrease PCl3, this will cause the equilibrium to shift towards products. If you increase chlorine gas, this will cause the equilibrium to shift towards reactants. And if you decrease the chlorine gas, it will cause the equilibrium to shift towards products. All right, now we're going to try to do one ourselves. Predict any shift in equilibrium for each of the changes of the reaction. So NH4HS, solid, produces H2S gas and NH3 gas, and we're predicting whether we add or remove one of these, whether it shifts the reaction towards products or to reactants or not at all. So if you add H2S gas, that is a product, so it will shift the equilibrium towards reactants. NH4HS solid is added. This will not change anything because solids are not included in equilibrium expressions. However, if you remove ammonia from the system, this will shift the equilibrium towards products, as will a removal of H2S gas. Another thing you can do to stress the system is decrease the volume. So if you decrease the volume, this increases the concentration, which can upset equilibrium as well. So say you have A in the gas phase, and it's going to B and C in the gas phase. There are 6 moles of A, 2 moles of B, and 2 moles of C for a total of 10 moles. And then you compress the system. So the system will act to decrease its concentration, which will cause less moles of B and C to be present and more moles of A to be present, because 1 mole of A produces 2 moles of gas, and as we know from our gas lectures, the more moles of gas you have, the higher the concentration. So the first equilibrium has 10 moles of gas present. We've decreased the volume, and now there are only 9 moles of gas present, because reducing each of the products by 1 mole only increases the reactants by 1 mole. So when a reaction in equilibrium contains different numbers of moles of reactants than products, a decrease in volume will increase the concentration, upsetting equilibrium, and therefore the equilibrium will shift towards the fewer number of moles. Here is another example here of nitrogen gas reacting with hydrogen gas to produce ammonia gas. There are more moles on the reactant side, so a decrease in volume will push the reaction towards the products which have fewer moles. And in fact, when this process is done industrially, one of the things they do is compress these two gases together and apply a large amount of heat, and this produces ammonia, which can then be used to make fertilizer. So, if you conversely increase the volume, this will shift the equilibrium towards the side with the greater number of moles. So, in the same reaction of A going to B and C, there are 11 moles present after you've increased the volume from the equilibrium state where there are 10 moles present. So you have 6 moles of A, 2 moles of B, and 2 moles of C as before, with a total of 10 moles. You've increased the volume, you've increased the space available for molecules to exist, and therefore the number of moles of B and C can increase, and the number of moles of A will decrease, increasing the total number of moles of gas. So when a reaction at equilibrium contains different number of moles of reactants than products, an increase in volume will decrease the concentration, which will upset the equilibrium and shift the equilibrium towards the greater number of moles. Now we get into heat. So there are two types of reactions that involve heat, exothermic and endothermic. An exothermic reaction will release heat, so a decrease in the temperature will remove heat and the equilibrium will shift towards the products. If you increase the temperature, this adds heat and the equilibrium will shift towards the reactants. So in the case of nitrogen plus hydrogen, if you decrease temperature, then more ammonia will form and also heat will be evolved. If you increase the temperature, the reaction will run in reverse. So in order to make this reaction happen, you have to dissipate this heat somehow, or the temperature will continue to rise and cause the reaction to go in reverse. So here's a summary using our good old sulfur trioxide and sulfur dioxide and oxygen reaction. So if you increase the temperature of this exothermic reaction, this will cause less product to form, which will decrease the equilibrium constant value. If you decrease the temperature, then more product will form. This will shift the equilibrium by increasing the Kc value. And then with endothermic reactions, a decrease in temperature will remove heat and the equilibrium will shift towards reactants, and an increase in temperature will add heat and the equilibrium will shift towards products. So calcium carbonate plus 133 kilocalories of heat will break down into calcium oxide and carbon dioxide. Increasing the temperature will make this reaction go quicker, and decreasing the temperature will make it go towards reactants. And here is a summary using a different reaction of involving nitrogen, oxygen, and nitric oxide. This is also endothermic. So an increase in temperature will cause the equilibrium to shift towards more product and less reactant, which will increase the Kc value. And a decrease in temperature will cause the equilibrium to shift towards less product and more reactant, which will decrease the Kc value. And here is a summary of all the different condition changes and their effect on equilibrium. So if you have a concentration condition, if you add a reactant, it will cause the reaction to move in the forward direction to remove stress. If you remove reactant, it will cause the reaction to move in the reverse to remove the stress. And conversely, if you add product, it will cause the reaction to move in reverse to remove the stress. And if you remove product, it will cause the reaction to go forward to remove the stress. If you change the volume by decreasing it, this will cause the reaction to move towards fewer moles in the gas phase. If you increase the volume, it will move towards more moles in the gas phase. And for endothermic reactions, raising the temperature causes the reaction to go forward. Lowering it causes the reaction to go in reverse. And exothermic reactions, if you raise the temperature, the reaction will go in reverse. And if you lower the temperature, the reaction will go forward. Catalysts do not change the rates, do not affect equilibrium because they increase both rates equally, and therefore it doesn't stress the system. So here is a learning check using the breakdown of nitrogen dioxide plus with heat to nitrogen monoxide and oxygen gas. So indicate how the equilibrium will shift in light of each change. So if you add NO, it is a product, so it will shift the reaction towards reactants. If you add NO2, that is a reactant, so it will shift the reaction towards products. If you lower the temperature, that removes heat from the system, which will reduce the rate in the forward direction and shift the reaction towards reactants. If you remove oxygen, that reduces the concentration of products, which causes the rate of the forward reaction to increase. And if you increase the volume, the X to reduce or to maximize the number of moles in the gas phase, so it will shift towards products, where there are 3 moles of gas instead of 2. So we can also apply equilibrium constants to solutions. So something called a saturated solution contains the maximum amount of dissolved solute, and it will also contain solid solute. This makes it an equilibrium system where the rate of dissolving is equal to the rate of recrystallization, and there is an equilibrium between the solid and the ions in solution. So this allows us to define something called the solubility product, or KSP, and this gives ion concentrations at a constant temperature. This also does not include solids because the concentration of the solid is constant. So the example shown here is iron hydroxide, which is a solid, dissolving to produce iron 2+ and 2 hydroxide ions. The KSP for this reaction is just the products. Concentration of iron times the concentration of hydroxide squared. So write some KSP values for each of the following: iron sulfide, silver carbonate, and calcium iodate. So iron sulfide breaks down into iron and sulfide ions. So the equilibrium constant expression is just the concentration of iron times the concentration of sulfide. Silver carbonate is a bit more complicated. It breaks down into 2 silver ions and 1 carbonate ion. So the expression is silver concentration squared times carbonate concentration. And then calcium iodate is 1 calcium ion and 2 iodate ions. So the expression is calcium concentration times iodate concentration squared. Just like before, we can make a flowchart for anything. So calculating KSP values, you write the equilibrium equation for the dissociation of the ionic compound. Then you write the solubility product and substitute molarities of each ion into the KSP expression and calculate. So calculating the solubility product constant for lead sulfate, which has a solubility of 1.4 times 10 to the minus 4 molar. You write the equilibrium equation for the dissociation. So in this case, it's lead sulfate solid going to lead ions and sulfate ions. Solubility product is then the concentration of lead times the concentration of sulfate. And Then we can calculate our KSP value by multiplying those two given concentrations by each other. If the solubility is 1.4 times 10 to the minus 4, and the dissociation produces 1 mole of each ion, then the concentration of each one of them is 1.4 times 10 to the minus 4 molar. You multiply those two together, and it's 1.4 times 10 to the minus 8 for the solubility product constant. Here are a number of solubility product constants for some commonly encountered salts. Notice silver chloride has a very low solubility constant, as does silver sulfate. Barium carbonate also has a low one. Barium sulfate is low. Calcium fluoride is low. Calcium hydroxide is fairly insoluble. All of these are very insoluble because they're specifically compounds of silver and lead are always insoluble. And alkaline earth are insoluble when they're combined with these ions. So we're going to use these KSP values to come up with some useful information. What is the KSP value for lead fluoride if the solubility at 25 degrees Celsius is 2.6 times 10 to the minus 3 molar? You have three options: 1.4 times 10 to the minus 5, 6.8 times 10 to the minus 6, and 7 times 10 to the minus 8. So first, we write our equilibrium equation. Lead fluoride dissociates to lead 2 plus and 2 fluoride ions. So our solubility product expression is concentration of lead times the concentration of fluoride squared. And therefore, we are given the concentrations of both. Well, we know that the solubility is 2.6 times 10 to the minus 3 based on this. We also know that if 2.6 times 10 to the minus 3 molar lead ions are produced, there's twice as much fluoride, so there's 5.2 times 10 to the minus 3, and we have to also square that. So this product is equal to 7.0 times 10 to the minus 8, which is option 3. Now, the molar solubility is then the number of moles of solute that can dissolve in 1 liter of solution. And we calculate this from the KSP value. And shown here is an insoluble salt, cadmium sulfide. So steps for calculating your molar solubility from KSP values: write your equilibrium equation for the dissociation of the ionic compound, write the solubility product expression for KSP, then substitute S for the molarity of each ion into the KSP expression and calculate the molar solubility. So for example, if you want to find the molar solubility of strontium carbonate, it has a KSP value of 5.4 times 10 to the minus 10. So you write out the equilibrium equation. Strontium carbonate dissolves to form strontium ions and carbonate ions. The solubility product is concentration of strontium times the concentration of carbonate. And we know that they're equal to each other because they're at a 1-to-1 ratio. So the concentrations are S times S, or S squared, is equal to 5.4 times 10 to the minus 10. You solve this by taking the square root. So the square root of 5.4 times 10 to the minus 10 is equal to 2.3 times 10 to the minus 5 molar. Another example, calculate the molar solubility of lead sulfate. If the solubility product constant is 1.6 times 10 to the minus 8. And the options are 1.3 times 10 to the minus 4, 4.0 times 10 to the minus 4, and 2.6 times 10 to the minus 16 molar. So we start by writing the equilibrium equation. Lead sulfate goes to lead and sulfate. The solubility product is the concentration of lead times the concentration of sulfate. And substituting S for each molarity gives us S squared is equal to 1.6 times 10 to the minus 8. Taking the square root of 1.6 times 10 to the minus 8 gives us 1.3 times 10 to the minus 4 molar, which is answer 1. And this concludes our discussion of reaction rates and equilibrium. It's a lot to digest, but hopefully you are starting to see how all of the concepts relate to one another. And once we get into acid-base chemistry, this will all tie together in a big way. So keep an eye out for the quiz on solutions, and also the next lab, which will talk about soluble and insoluble salts.